Let's look at the stereoselectivity of the E2 elimination reaction. So here I have my alkyl halide, right? And I know my alpha carbon is the one that my halogen is bonded to. And I know my beta carbon is the one right next to it. So there's a beta carbon right over here that has two hydrogens on it. And then there's a beta carbon over here as well. And we will worry about the beta carbon on the left in a few minutes. For right now, we want to focus on the beta carbon on the right. And the beta carbon on the right has two protons on it. So there are two protons that could participate in this mechanism, and you'll see when we start drawing Newman conformations, those two protons are going to allow two different possible conformations, and so we can get a few different products, and one stereoisomer is going to be favored, and that's the concept of stereoselectivity. Alright, so let's draw our Newman projection. So we're going to put our eye right here, and we're going to stare down the alpha-beta bond, right? So we're going to stare down this bond right here. So now we're going to try to draw the Newman projection for what we would see. So you can get out your molecular model set if you have a hard time with this. And there was an earlier video on drawing Newman projections. So we're staring right at this carbon right here, and there's a bromine going off to the right. And then there's a hydrogen going off to the left. And then there's a methyl group going down. So let's just identify those real fast. Right? Bromine going to the right, hydrogen going to the left, and then a methyl group going down. So now we move on to our beta carbon right here. So we represent that with a circle on our Newman projection. So here's our circle. What's coming off of our beta carbon? Well, there's a methyl group going up. So we can go ahead and draw our methyl group going up like that. And then we have two hydrogens, one going to the right and one going to the left. So a hydrogen going to the right and a hydrogen going to the left, like that. All right, so let's redraw this Newman projection. And what we're going to do is we're not going to rotate anything. We're just going to say, okay, I'm going to just change it a little bit. I'm going to make the bromine at the very top, and then I'm going to put this hydrogen right here at the bottom. Okay, so again, I'm not going to show any change of conformation yet. Right now, I'm just going to put that bromine at the top. So if I put the bromine at the top of my Newman projection, what will I get? Well, I still have this carbon, a hydrogen to the left of the bromine coming off of that carbon, and then a methyl group going off to the right. And for my carbon in the back here, I have a methyl group between the hydrogen and the bromine, so I go ahead and put my methyl group in there. And this is a hydrogen, and then this is a hydrogen. So again, I haven't done any rotation yet. I've just changed my viewpoint. So here I have my Newman projection. And we could even draw this in a sawhorse projection, so it's even a little bit easier to see. So let's go ahead and draw it in a sawhorse projection. So there's my front carbon. So let me go ahead and draw in my bonds in my front carbon. And then my back carbon is going to be back here, shaped like a Y this time, so it's going to look something like that. All right, so on my front carbon, right, there was a bromine going up. There was a hydrogen going to the left, and there was a methyl group over here. And on my back carbon, this was our methyl group, so let's see if we can squeeze that in. And then this was a hydrogen, and then this was a hydrogen. So now that we've drawn all of that, we're ready to go ahead and think about our mechanism. And we know that sodium ethoxide is a base. Right, so the negative charge on the oxygen is going to take a proton. And the proton that's going to take is the one in the anti-periplanar conformation. So it's easy to see now that we've drawn out our sawhorse projection and we have our Newman projection here. So the proton that's in the anti-periplanar conformation, it's the one in the same plane as your bromine. So if you're looking over here at your Newman projection, right, this is your bromine, and then this would be your beta hydrogen in the anti-periplanar conformation. So if we go over here on the sawhorse projection, right, that would be this hydrogen and this bromine. So they're in the same plane and they're on opposite sides from each other. So that's where the anti comes in. So if we're going to go ahead and draw the mechanism, we're going to show our base taking this proton Right, so it's going to take this proton, leave these electrons behind, which are going to move in here to form your double bond, and then your bromine is going to be your leaving group, like that. So if we were to draw the product of this reaction, it's going to be an alkene, and when we draw our products, we can see that our two methyl groups are going to be on opposite sides of our double bond. That might be even easier to see over here on your Newman projection. So the double bond would form between your front carbon and your back carbon here, and your methyl groups will end up on opposite sides from each other. So let's go ahead and draw what that would look like. All right, so I'm going to form a double bond right in here, and this methyl group is going to be on that side, and then this methyl group is going to be on that side. So I just formed the trans stereoisomer, right? So this is the trans stereoisomer, like that. And that's one of the possible products that could form from this beta carbon. But remember, we had another beta proton to worry about. So let's go back to our Newman projection over here on the right, and let's see if we can show some rotation to look at yet another proton. So remember, these are all single bonds at this point, and single bonds allow free rotation. So I could show the methyl group. I could show the back carbon rotating. So let me go ahead and do that. Let me go ahead and draw what I'm looking at here. So if I wanted to show this methyl group right here, I'm just going to rotate the back carbon. So I'm going to move this methyl group over here to this position. Okay, so let's go ahead and draw what that would look like. I'm going to keep the front carbon still. So I'm going to keep the front carbon still. So I'm going to go ahead and draw in my bromine here, and then my hydrogen, and then my methyl group, like that. And then the back carbon I've now rotated. Okay, so rotate the back carbon. I rotated it so the methyl group ended up over here now. So if the methyl group rotated over there, that means this is now a hydrogen, and that means that this is a hydrogen. Okay, so another possible conformation. And if I think about where my anti-periplanar proton is now, right, you can see that this is now my proton in the same plane as my bromine. So if I were to draw a sawhorse projection for this one, let's go ahead and do that. Let's draw a sawhorse projection for this one. Makes it a little bit easier to see this. All right, so here is my front carbon, and it looks like this, and then my back carbon is going to be shaped like a Y again. Okay, so I put in my groups here. I know my bromine is right here. I know that this is a hydrogen. I know that this is a methyl group. And then on my back carbon, I know that this is a hydrogen. I know that this is a methyl group. And I know that this is a hydrogen. So for my mechanism, I'll go ahead and draw in my ethoxide anion. I know that my ethoxide anion, right, is negatively charged. It is going to take the anti-periplanar proton, which on my sawhorse projection is of course this guy once again. So it's going to take that proton, so I'll show the negative charge taking that proton here, and once again these electrons are going to move in here to form a double bond, and our halogen is going to leave all at the same time. So what product would we get from this? Well, if I look at my methyl groups this time, right, if I look at my methyl groups this time, I think it's obvious that this methyl group is kind of on the same side as this methyl group. Right? If you're thinking about the formation of the double bond, it might be a little bit easier to see it right here in the Newman projection. Right? The two methyl groups are on the same side. So when I'm showing the product, right, I can show my double bond form right in here. And then this time, my two methyl groups are going to end up on the same side. So this, of course, is the cis product. So I have the trans product, I have the cis product, and which one of these is my major product? Well, we talked in an earlier video about how the trans product is going to be the most stable, right? So this is going to be the major product because of steric hindrance. And it's easiest to see on your Newman projections here, right? If I go back to my Newman projections, and I'm looking at this methyl group, right, being anti to this methyl group, that's as far away as they can get from each other. So that's the favored conformation. So if you're talking about these two conformations going back and forth, right, the arrow would be larger going to the left because this is more stable. So a smaller arrow here going to the right. And On the right, my two methyl groups are gauche to each other, right? They're relatively close to each other, so that's a lot of steric hindrance. So the conformation on the right isn't as favored as the conformation on the left. Therefore, your trans product is going to be major, and your cis product is going to be the minor product for this reaction. There's still one other product that could possibly form, and that comes from the other beta carbon that we talked about, right? So if I go up here, all of that we just did, all we just did there took care of these two protons, right? And showed us the stereoselectivity of this reaction for the trans stereoisomer. But there's another beta carbon over here with beta protons. So there's actually one more product, and this is the easy one because we don't have to worry about drawing all these complicated Newman projections. Okay, so let's redraw the reaction really fast. And I don't even have to worry about stereochemistry, so I won't even bother with it. I'll just put in my bromine there. And we know that this is my alpha carbon, and then this is my beta carbon. And we know there are a bunch of beta hydrogens there, so I'll just pick one. I'll just say this is my beta hydrogen. And once again, our sodium ethoxide base comes along, right? So let's go ahead and draw that in here. There's the ethoxide anion. So it's going to take this proton, right? These electrons are going to move in here, and the bromine is going to leave. So we are going to get this as our product, the double bond forming between our alpha and our beta carbon. So this is a mono-substituted alkene, right? So this is mono-substituted alkene. So this is going to be extremely minor, right? So this is really going to be the minor product of this reaction. This is mono-substituted versus these trans and cis stereoisomers. They are di-substituted, so we know that trans and cis are going to form in larger quantities than this mono-substituted product. So that's the stereoselectivity of the E2 elimination reaction.